Hi guys, welcome back to my channel. So today what we're going to be looking at is some integration using the Trig identities. And why would we use the Trig identities to integrate something? And it's simply because we want to make it easier for ourselves. So we're going to substitute in values that are going to be easy to integrate. We know that if we have a product function, that when we find the derivative of that function, that's actually a pretty complex procedure. And doing the antiderivative of that is going to be even more complex, trying to work backwards. So if we substitute in these values here, see how we've got a sine squared x, we can get rid of that whole sine squared business by just dealing with these linear trig functions. I shouldn't say linear trig functions, I should say trig functions with 1 as their highest power. So it makes it a lot easier for us to integrate them. So let's go ahead and let's do some simple examples. And I may have to scroll back up to these trig identity functions a few times. I think, what page are these on in your textbook? These are on page 341 if you wanted to work out where they are. Because I know sometimes when you search trig identities online, they have like every which way identity and you don't always need all that information. So that's page 341, just so you guys are aware. All right, so this first question on page 350 is actually asking you to find the derivative of cos 2x. Now, I kind of admitted in my last video that I never really remember all of like sine goes to cos or cos goes to sine or all of that for the derivatives and for the integrals. I only really remember one, and the one that I remember is that sine goes to cos when I derive. And so everything else I can glean from that one piece of information. Because I don't have that much space in my brain. So to find this derivative, it's just going to be equal to negative sine 2x multiplied by 2. Because that's the derivative of the inside function. And that is all we have to do. So very, very simple example. Okay, so let's have a look at this one now. So cos squared x. Now this one, it's asking us to find the integral of cos squared x with respect to x. So this one now is getting into the integration side of things, not the derivative side of things. So what I'm going to do is I'm going to write my little memo up here for myself. So this is the one I remember. So the derivative of sine is going to go to positive cos. I only remember this one, and everything else stems from that one, because I know that the derivative of cos is then going to go to negative sine. I know that the integral of cos is going to go to sine, because this is the reverse of this process, and the integral of sine is going to go to negative cos, because that's a reversal of this process. So like I said, I just remember this one, and then the rest of them sort of come from that. Okay, so what we're going to do, we're going to scroll up to those trig identities now, and we can see here that this is going to be equal to this function. And for us, x is just going to be equal to 1. So that makes it nice and simple for us. So if we substitute that value in instead, we're going to get the integral of 1/2 multiplied by 1 plus cos 2x, because we've doubled that value inside the bracket. Okay, so let's go ahead and let's expand these brackets now. And this is going to be the integral of 1/2 plus cos 2x over 2. And we're still going to derive with respect to x. Okay, so now the integral of 1/2 is just going to be 1/2 x, or x on 2. Oh, I don't need to write that integral sign, so that's just going to be x on 2. Now, cos, when we integrate cos, that is going to go to positive side. So this is going to go plus sine 2x. Now, when we found the derivative of this, we found the derivative of inside function and multiplied by the derivative of the inside function. So now we're going to divide by the integral of the inside function and then add 6. All right, so let's move on and let's do another simple example using those trig identities. All right, so this is question 2D. So just quickly again, we're going to use our trig identities. So if you just flick back to that page 341, we're now going to be using this expression here. So sine squared ax is equal to 1/2 1 minus cos 2ax. Okay, so let's substitute, or let's write that formula over here first so that we know. So sine squared of ax is going to be equal to 1/2 times by 1 minus cos 2ax. Okay, so in this case, our a is going to be equal to 3. So keep that in mind. And this value at the front here, we can actually just move that outside the integral. So now we would be dealing with 4 multiplied by the integral of sine squared 3x. So let's substitute this in place for sine squared dx now. So we're going to find the integral of 1/2 multiplied by 1 minus cos 2ax. In this case, we're going to double this inside function here. So that's going to become 6x. And we're still integrating with respect to x. And again, we can move this half out the front here. So we now have the integral of 2 lots of 1 minus cos 6x dx. Okay, so the integral of 1 is just going to be x. X times 2 is 2x. The integral of negative cos is going to be negative sine, and then we're going to divide that by the derivative of the inside function, and then we're going to times that by 2. Maybe I should do this in part steps. So we're going to do negative sine, because cos goes to sine, and so negative cos will go to negative sine. Then we divide that by the derivative of the inside function, and then we're going to times that by 2 and then add c. So let's simplify that. So we get 2x minus 1/3 sine 6x plus c. So there we go, another simple example. I might do one more example of a simple familiar question for you. So this is going to be a fun one. I like the look of this one. So it's a little bit more complex than the last examples, but it's still an example of a simple familiar question. Because cos to the power of 4 is really just the same as saying cos squared, right? So we could rewrite this as the integral of cos squared 3x squared dx. And so now what we can do is we can use that same value as before. So if we have cos squared ax, that's going to be equal to 1/2 times by 1 plus cos 2ax. Okay, so in this case, our a is equal to 3. So we're going to have to double that when we replace this. So this is going to be the integral of, maybe I should do some funny brackets. So the integral of 1/2 times by 1 plus cos, double this value in here, cos 6x, and then we're going to square that, and then integrate with respect to x. So let's expand this out and let's simplify this. So just to show you what I've done. So first things first, I distributed this 1/2 across the brackets. Then the next thing I did was I squared this, and I just did this by hand. So I thought this was a bit complicated to do in my head. So I did write out the double brackets, and I did expand just using the FOIL method. And then I just collected my like terms. Now, here's the issue though. When I've done this, I've still ended up with a cos squared value. So how do we now deal with this? Well, we deal with it in the exact same way. We go ahead and we replace it. So let's do this on this next line here, because this is getting a little bit more complicated now, because this is going to be cos squared 6x over 4. Okay, actually, maybe what we can do just to make it a little simpler is we can put this 1/4 out the front here, and then that's going to give me 1. That's going to give me 2 cos 6x, and then that's just going to give me 1 cos. So that might be a little bit easier actually for me to deal with. Okay, so I'm just going to fix that up a little bit better. It's just bothering me. Just me being a bit of a Nazi about it, but it's fine. Let's, hold on, here we are. Getting all over the shop, aren't I? 1 plus cos, and we double that value, 12x. Okay, so we're going to substitute that now back into our equation, and I'm going to distribute this 1/2 across the brackets. So we have our 1/4 at the front, and this is going to be 1 plus 2 cos 6x plus 1/2 plus cos 12x over 2 dx. And again, I could factorize out another half, so I have an eighth times by all of this, and then I won't have to deal with fractions. That's up to you. We can go ahead and integrate this now because the highest power of cos is just 1, and it's a nice simple integration because we know when we integrate cos, it's going to go to sine. I'm just going to give myself some space. So I'm just going to continue working over in this little zone here. So this is going to become x plus, now I'm going to do this the slow way because this is getting complicated. So 2 sine of 6x over 6. If you can simplify that quick in your head, then please be my guest. Oh, I should have combined my like terms because 1 plus a half makes 1 1/2. And so I could just change this. There we go. Nice and easy. Plus cos 12. So this is the same as saying a half times by sine of 12x divided by 12 plus c. Okay, so let's simplify this now. So I'm not going to bother popping through that quarter just yet. So 3x over 2 plus 1/3 sine 6x plus 1/24 sine 12x plus c. Now I'll apply this 1/4 and I'll distribute that across the bracket. So that's going to give me 3x over 8 plus sine of 6x over 12 plus sine of 12x over 48 plus c. So I've just gone and checked the answers and I just realized I've made a stupid mistake here. So 1/4 times by 1/24 is not 48 because it's not 12. It's going to be double that amount. That was silly on my behalf. So this should be over 96. And I've just quickly gone back and checked in the answers that I've done that correctly. Okie doke. So that is how to integrate some simple functions using trig identities. And I know this last example got a little bit more complex, but really it just comes down to this idea that when we have even powers of cos, or like cos to the power of 2, cos to the power of 4, cos to the power of 8, things like that, then really all we're doing is just squaring a square. And so we just have to go back in and resubstitute in that trig identity again and again. Alrighty guys, so I hope you enjoyed this video and I will talk to you again soon. See you later.